Dark matter is not just important on the scale of galaxies. It played a critical role in the early universe itself. Shortly after the Big Bang, the universe was hot, dense, and nearly uniform. Tiny fluctuations in density existed, but on their own, normal matter would not have clumped together fast enough to form the structures we see today. Dark matter changed that. Because dark matter does not interact with light, it began clumping earlier than ordinary matter. While radiation pushed normal matter apart, dark matter responded only to gravity. These early dark matter clumps acted like gravitational seeds. Normal matter later fell into these regions, forming the first stars, galaxies, and clusters. Without dark matter, galaxies would likely never have formed at all. This makes dark matter not just a mystery, but a requirement for the universe as we know it. One of the strongest pieces of evidence for dark matter comes from an object known as the bullet cluster. The bullet cluster is the result of two galaxy clusters colliding. When the clusters passed through each other, their hot gas clouds collided and slowed down. This gas contains most of the visible mass. But gravitational lensing showed that most of the mass passed straight through without slowing. The mass did not follow the gas. It followed something invisible. This separation between visible matter and gravitational mass is difficult to explain without dark matter. Modified gravity theories struggle to account for this observation. For many scientists, the bullet cluster is one of the clearest demonstrations that dark matter is real. Another way dark matter reveals itself is through how galaxies evolve over time. Spiral galaxies, like the Milky Way, are surrounded by enormous halos of dark matter. These halos extend far beyond the visible stars. They help stabilize the galaxy's rotation. They influence how stars move. They shape the galaxy's long-term structure. Simulations show that without dark matter halos, spiral galaxies would be unstable and short-lived. Dark matter also affects how galaxies interact and merge. When galaxies collide, their dark matter halos merge first, guiding the visible matter that follows. This invisible framework shapes the cosmic web, the vast network of filaments connecting galaxies across the universe. Some scientists have asked whether dark matter might not exist at all, and whether gravity itself behaves differently on large scales. These ideas fall under modified gravity theories, such as MOND. Modified gravity can explain some galaxy rotation curves, but it struggles to explain large-scale structure, the cosmic microwave background, and galaxy clusters simultaneously. So far, dark matter explains all of these observations within a single framework. That does not mean the case is closed. Science remains open to better explanations. But any alternative must match decades of precise data. As technology improves, new experiments continue to search for dark matter in different ways. Some look for signals from dark matter annihilation in space. Others search for subtle effects in particle accelerators. Astronomers study dwarf galaxies, which are especially rich in dark matter. Each approach explores a different possibility. So far, dark matter has remained elusive, but its gravitational fingerprints are everywhere. It shapes the universe on the largest scales. It determines how galaxies form. It influences the fate of cosmic structures billions of years into the future. Dark matter does not interact with us directly. It passes through our bodies constantly without notice. Trillions of dark matter particles may be passing through you every second. They do not collide with atoms. They do not leave a trace. They simply move through space-time, responding only to gravity. This makes dark matter both ordinary and strange. It is everywhere, and yet completely invisible. As research continues, future discoveries may finally reveal what dark matter is made of. Or they may force us to rethink our understanding of physics entirely. Either outcome would deepen our understanding of the universe. For now, dark matter remains one of the strongest examples of how much we can know without ever seeing. Gravity tells its story. Structure reveals its presence, and the universe itself bears its imprint. Dark matter is not something distant or abstract. It plays a direct role in the galaxy we live in. The Milky Way is embedded in a vast halo of dark matter that extends far beyond its visible disk. This halo is several times larger than the galaxy itself and contains far more mass than all the stars, planets, gas, and dust combined. As the Milky Way formed, dark matter was already present. It gathered first, forming a gravitational well that normal matter later fell into. Gas collected, cooled, and eventually ignited into stars. Without this dark matter halo, the Milky Way would not have formed in its current shape. Its spiral arms would not be stable. Its stars would not move in the orderly orbits we observe. When astronomers measure how stars orbit the center of the Milky Way, they find the same pattern seen in other galaxies. Stars far from the center move faster than visible matter alone can explain. This motion is one of the clearest signs that our galaxy is dominated by dark matter. Dark matter also influences the small satellite galaxies that orbit the Milky Way. These dwarf galaxies are some of the most dark matter-rich objects known. They contain very few stars, yet their stars move as if surrounded by enormous mass. This makes them valuable laboratories for studying dark matter's behavior. Some of these dwarf galaxies appear to be almost entirely made of dark matter, with stars acting like faint tracers of an invisible structure. Dark matter even affects how the Milky Way interacts with neighboring galaxies. When galaxies approach each other, their dark matter halos interact first, shaping the path and outcome of the encounter. The future collision between the Milky Way and the Andromeda Galaxy will be guided largely by their dark matter halos. Long before the stars collide, the invisible structures will merge. On even larger scales, dark matter connects galaxies across the universe. It forms long filaments stretching millions of light years, intersecting at dense nodes where galaxy clusters form. Between these filaments are vast cosmic voids, regions with very little matter at all. This web-like structure is a direct result of dark matter's gravitational influence over billions of years. The cosmic microwave background also carries the imprint of dark matter. This faint radiation, left over from the early universe, shows tiny temperature variations that match predictions made by dark matter models. These patterns reveal how matter was distributed when the universe was only about 380,000 years old. They show that dark matter was already shaping the universe long before the first stars existed. Despite its importance, dark matter remains one of the most challenging problems in modern physics. Decades of experiments have not yet identified its true nature. Some scientists are now considering more complex possibilities. Dark matter might consist of multiple types of particles. It may interact with itself in ways we do not yet understand. There is also the possibility that dark matter behaves differently at different scales. It may appear cold and slow-moving in some contexts, while acting differently in others. Future observatories and experiments may finally detect dark matter directly. New detectors will be more sensitive than ever before. Astronomers will map dark matter with greater precision using gravitational lensing surveys. Particle physicists will push the limits of detection deep underground and in space. Each experiment narrows the possibilities. Even if dark matter remains undetected for many years, its existence is firmly supported by evidence. It explains observations across time, space, and scale. Dark matter reminds us that the universe is not limited to what we can see. Most of reality operates quietly, invisibly, shaping everything from the shadows. Understanding dark matter is not just about solving a mystery. It is about understanding how the universe came to be structured the way it is. It tells the story of how chaos became order, how gravity sculpted matter into galaxies, and how invisible forces govern the visible cosmos. As science continues forward, dark matter remains one of the clearest signs that the universe is deeper, richer, and more complex than our senses alone could ever reveal. And that realization, more than any single discovery, is what makes the study of dark matter so profound.